Welcome to the 2015 NASA Ames Summer Series. In mission design, as in life, we tend to study lots of risks. But also, as we design the mission, as we go through life, we also take certain items for granted. Because we take them for granted, usually they can develop into being a big risk. One such area that we take for granted every single day is the sun. The sun is important for life. When we look for habitable planets, we look at the energy that the star that the planet surrounds creates to say, is it habitable? In modern society, we have lots of things that are dependent, lots of satellites, your TV, your GPS, that are dependent on space assets. They're not protected by the atmosphere that is here on Earth. So the sun is critical for that area. Today's talk, entitled Sending a Probe into the Atmosphere of Our Sun, will be given by Dr. Justin Kasper. Dr. Kasper is an associate professor at the University of Michigan and a researcher at the Smithsonian Astrophysical Observatory. He earned an AB in physics from the University of Chicago and a PhD in physics from a small institute called the Massachusetts Institute of Technology. He is the principal investigator of the SWEEP investigation, which you will hear about today. He also received in 2010 the Presidential Early Career Award for Scientists and Engineers. And in 2011, he was awarded by Popular Science magazine as the brilliant 10 to watch for. Please join me in welcoming Dr. Justin Kasper.
Thank you for that introduction. It's great to be here. So what I want to do today is talk to you about our plans to send a probe into the atmosphere of our own sun. So in 3 years, actually to the week, we're going to make history by sending an instrumented probe for the first time into the atmosphere of our sun. This is going to enable us to make unprecedented observations of the sun's atmosphere. It's also obviously an incredible technical challenge, devising a spacecraft and instruments that can survive these close encounters with the sun. So what I want to do today is I want to give you a flavor of the why and the how. So why are we building a probe to enter the sun's atmosphere? What's so pressing? Why do we need to do it now? What questions are we trying to answer? And how are we going to go about doing it? At closest approach, the front of the spacecraft is going to be absorbing megawatts of sunlight from the sun. Exposed surfaces will be heated to 1,500 degrees Celsius. The whole front of the spacecraft and sun-exposed instruments will actually be glowing red to the eye. So that's obviously a very unusual environment for a spacecraft. It's not like anything we've had to deal with before. And so this presents certain very specific technical challenges, including how do you convince yourself that your design for an object that can actually survive that environment is going to actually work? Now, before I get into the why and the how, I do want to spend a little bit of time talking about the who. So, you know, I'm here today to talk about Solar Probe, but I'm just one of many people working on this project. There are hundreds and hundreds of scientists, engineers, and supporting staff across the country that are responsible for this amazing mission that I'm fortunate enough to get to talk to you about today. If you're curious, Solar Probe is part of what we call the Living with a Star program at NASA. The mission itself is led by Johns Hopkins University's Applied Physics Lab, and the Living with a Star program is coordinated at Goddard Space Flight Center. But there are more than 40 institutions that are playing a role in the science, in the instrumentation, in the observing plans, and in the theory that we need for this mission. My part of the project is called the Solar Wind Electrons, Alphas, and Protons, or SWEEP investigation. Turns out the solar atmosphere is predominantly made of fully ionized hydrogen and helium, or the slang for that is alphas and protons. So electrons, alphas, and protons are bread and butter, and that's what our investigation is measuring. And that part of the project we lead out of the Smithsonian Astrophysical Observatory, Berkeley Space Sciences Lab, relatively nearby, University of Michigan, NASA, and other partners around the country. So I'll be telling you about this project, and I'll just give you my little particular sliver of experience. There's a lot of amazing stuff going on Probe. So let's start with the why. Why send a probe into the atmosphere of the sun? And you know, here's a photograph of a base camp at Everest. I know the first thought might be, well, why not, right? Isn't part of NASA's responsibility, isn't what we're interested in just to go new places, you know, to do things that are hard? There are definitely a lot of very hard aspects to a solar probe mission. It's very exciting. I mean, I really enjoy getting to tell people about all the new technology we've had to develop just to do this mission. But that's not the only reason we're doing this. There's some very basic scientific motivations, some scientific puzzles that have actually been around for more than 500 years. They'll only really appreciate it in the last 100 years. And then with our new dependence on infrastructure and space, our sensitivity to space weather, unfortunately, these mysteries about the sun can now influence society on Earth. And so it's become very pressing that we launch this probe. So beyond just the thrill of exploration, we have some very basic scientific reasons. So let's start with the why. And here's a picture taken by the Solar Dynamics Observatory in visible light of the sun a couple years ago. And so here's the sun. It's yellow, kind of boring, right? You know, just this yellow sphere. It doesn't seem particularly dynamic or interesting, right? If you went out on any day, this is what you'd see, right? Now, why is the surface of the sun yellow? Right? It's yellow because it's at a temperature of around 6,000 degrees Kelvin. So if you look at your toaster and you get those heating elements nice and hot, they'll start glowing yellow and orange. Right? This is called black body radiation. So every object in the universe emits radiation, and the wavelength of the radiation is inversely proportional to the temperature of the object. So right now, if I had like infrared goggles on, I could see everyone in the room just from the infrared light that you're giving off because your body's at room temperature. If you get hotter, you'll actually start to emit visible light. So you move from infrared into very dull reds, darker reds, oranges, and then yellows. And so the surface of the sun glows yellow because it's at a temperature of around 6,000 degrees. What you're seeing is the end product of the fusion happening at the core of the sun. So at the center of the sun, the pressure is so high, the density is so high that hydrogen fuses, making helium, releasing energy. That brings the temperature of the core of the sun up to more than 100 million degrees. And then just the further away you get from that heat source, the same way, you know, if you pull your hand away from an open flame, the cooler things get. The temperature slowly falls off the further away you get from the sun until you're out at the surface where things are a relatively balmy 6,000 degrees. And the only exceptions, just if you look carefully, you'll see every now and then there's some black splotches that appear on the sun. These are sunspots. Here's a nice zoom in of one of these sunspots. And what you see is a darker region. It turns out every now and then a big piece of magnetic field erupts from the surface of the sun. And that magnetic field is so strong, it actually stops the sun from boiling and churning there. And that piece of the sun's atmosphere cools off. And so it looks dark to us because it's not giving off that black body radiation. So sunspots are fantastic. But is this all there is to the sun? And the answer is going to be no. So, you know, it's difficult to look at the sun, right? I don't want to encourage anyone to go out there and stare at the sun right now. You know, it's so bright it can blind you. If you wear filters, you can look at the disk of the sun in visible light. But what you really want to do to understand the mystery of the sun is to be able to get a chance to see what's above this surface. Is there anything going on out here? Right? Today we can look with spacecraft that have special filters that block the disk of the sun, or look in wavelengths that are much brighter than emission from the sun itself. But if you went back 500 years ago, you had to wait for a particular alignment. So this is a painting from 1570 titled Astronomers Observing an Eclipse. And what they were taking advantage of is the fact that the moon is almost the exact same angular diameter of the sun in the sky. It's the size of your thumb if you stretch your arm out all the way, about half a degree. And so if you wait just for the right time and you're in the right place on Earth, for about 5-10 minutes, the moon will pass between you and the sun. You'll have an artificial night where the center of the sun is blocked out. And if you're patient and your eyes adapt to the dark, an atmosphere will start to appear around the sun, much fainter than the surface of the sun itself, so normally invisible. And even in old paintings and old records from 500 years ago, 1,000 years ago, people commented about how during an eclipse they were able to see rays of material coming out from around the sun. And so they called these rays a solar crown. And another word for crown, it was in Latin, it was the solar corona. And this stuck. So to this day we call the solar atmosphere, the extended solar atmosphere, the solar corona, to indicate the ray-like structure. And I'll show you some nice examples of that soon. Okay, so here's how you could observe the sun's atmosphere 500 years ago. What can we do today? Here's an eclipse seen from the International Space Station over Turkey in March of 2006. So this is a photograph taken by an astronaut looking down on the surface of the Earth just as the shadow cast by the moon blocking the sun passes over Turkey. And now I'm going to show you a photograph of the sun taken at the exact same instant in time by some astronomers in the center of that shadow, looking now up past the space station at the sun. Okay, and so if you squint, you may just be able to make out some craters on the moon. The moon's doing a perfect job blocking out the sun. And instead of the very intense light from the sun, we see these rays of material appear. So this is the solar atmosphere, the solar corona. And maybe you can see why, back in the Renaissance times, people called this the solar crown, this ray-like structure. And you can see it's a couple things. One, it's incredibly structured. You have some places where you just have rays of material coming straight out. You have other regions where it bunches together. If you're interested, what we're actually witnessing here is Thomson scattering of light. So white light from the sun is traveling out. It's striking material in the solar corona, and then that light bounces off. And so we're able to see that reflected light off of the material in the solar atmosphere. It's not actually emitting invisible light. It's just reflecting visible light from the sun. Okay, great. So people commented about these rays for hundreds of years. It's interesting the sun has an extended atmosphere. So what, right? Well, the scale height of that corona is a big problem. Although people didn't really appreciate this until halfway through the 19th century, around the American Civil War, where the concept of heat was first discovered in thermodynamics. Whoops, my equation isn't showing up there. Well, I can walk you through this. So if we assume the sun's atmosphere was in simple isothermal hydrostatic equilibrium, so all at one temperature, it's nice and symmetric. This is like the cow is a sphere level of approximations that physicists like to do. What you can do is you can derive an expression for how quickly the density of the solar atmosphere should fall off with altitude. The same way Earth's atmosphere, you get in an airplane, you go up to higher altitudes, the pressure gets lower and lower and lower, right? Well, you can derive the scale height at which Earth's atmosphere should half, and then half again, and then half again, just based on the mass of the typical molecule in our atmosphere and local gravity. You can do the same thing with the sun. And if you plug in the sun's gravity, which people had a good idea of even 150 years ago, and you plug in the 6,000 degree temperature of the surface of the sun, you get that the sun's atmosphere should fall off in half in density every 100 kilometers or so. Right, that's a real problem. Because if you look at these photographs, this material falls off, you're still seeing a lot of material entire solar radii away, even 4 or 5 solar radii away, about 1,000 times greater scale than a simple model would predict. Right, so there are only 2 possible conclusions then if you use the simple model of an atmosphere. Either the sun's corona is 1,000 times hotter than the surface of the sun, or the sun's atmosphere is made out of some new form of matter never before seen on Earth that weighs 1,000 times less than any normal matter that we've ever found on Earth. So at the beginning of the 20th century, people said, well, it's preposterous that the atmosphere could be hotter. We all know things get cooler the further away you get from a heat source. So there must be a new form of matter, and they called it coronium because it was what the solar corona was made of, and for a long time people were trying to hunt for evidence of coronium. It was only in the 1930s, as we started understanding the physics of high temperature materials, and techniques such as atomic spectroscopy that we finally realized that there isn't a new form of matter. Actually, what's happening is through some process that we still don't understand, the solar corona is heated to temperatures of 1 to 10 million degrees, so thousands of times hotter than the surface of the sun. That whole concept that we normally have that we're comfortable with on Earth, where the further away you are from a heat source, the cooler things get, seems to break down in the solar atmosphere. Things reverse and the temperature shoots up. Now, instead of waiting for an eclipse, what we can do today is we can use a spacecraft like the Solar Dynamics Observatory and look at the sun not in visible light, but in ultraviolet light. So as I said before, this black body radiation, the hotter an object is, the shorter and shorter wavelength it emits at. I said that this white light from the solar eclipse is not actually light given off by material in the corona, it's reflected light from the sun. The corona is pretty much invisible to our eyes. You need to be able to see in ultraviolet light. You need to see in wavelengths corresponding to material that's heated to 500,000 degrees, 1,000,000 degrees, before the corona actually appears directly. So this is a month of observations taken by the Solar Dynamics Observatory. We're looking at a wavelength of light that's 171 angstroms. It corresponds to plasma in the solar corona that's been heated to a temperature of about 500,000 degrees. And so what you can see is, far from a boring, simple sphere, the sun has an incredibly structured, incredibly dynamic atmosphere. I'll just highlight a couple features here. Can you see these loops? Right? And the loops are moving around, but they seem to pop up from one place and come down to another. So what you're seeing is a magnetic field that emerges from one sunspot, travels across the surface of the sun, and then descends down into another sunspot. And the reason we're able to see it is million-degree plasma is stuck on those magnetic field lines. Think of it as like when you look at a neon sign, right? And you can trace out a message in glass, and you fill the glass with a hot plasma that glows in visible light. Same thing's happening here. Somehow, and we don't really understand how, the magnetic field that emerges from sunspots is really good at heating plasma up to very high temperatures. It introduces magnetic fields into the sun's atmosphere, and that has something to do with the heating of the solar atmosphere and how the solar atmosphere gets its structure. And you can see it's very dynamic. You can see things are popping around constantly, new loops emerge, loops disappear. There's a lot of activity going on. Okay, so by the 1930s, people realized, even if they didn't know how the sun's atmosphere is heated 1,000 times hotter than the surface, they accepted that it was at 1 to 10 million degrees. But it was only in the 1950s that a theorist named Gene Parker realized that actually it's incredibly unstable to heat the atmosphere of a star up to these very high temperatures. In fact, if you look at those high temperatures, they're going to want to push the star's atmosphere away from the surface. Now, gravity is going to fight and try to contain that atmosphere, but what Parker showed is actually there's a regime of star masses and gravity and temperatures where the atmosphere not only wants to expand out, but that expansion is unstable. So the further away from the star that the corona expands, the faster it starts moving, it accelerates. So this was a plot from Parker's paper. Speed is a function of height above the surface of the sun. Once you're a few solar radii above the sun, this plasma is flowing at a couple hundred kilometers per second. It breaks the speed of sound. I'll break it to you. There is sound in space. The density is incredibly low, so the speeds are very high, many hundreds of kilometers per second. But the plasma breaks the speed of sound within a couple solar radii. By 10 solar radii, it's flowing faster than the fastest waves that can travel in a plasma, special magnetized waves we call Alfvén waves. And by the time you're out at 1 AU, you have a plasma that's flowing at about 10 to 20 times the speed of sound through space. And Parker called this a solar wind. And no one believed him. Paper kept getting rejected. Finally, an astronomer who was editing the Astrophysical Journal, which is where he published this paper, said, you know what, it's better to have a controversy out there. No one believes it, but no one can find an error in the math. Let's get it out there. Within a few years, the space age had started. Rockets had made it outside of Earth's atmosphere, and the solar wind was detected. Now, today I can actually show you the solar wind, because we don't have to wait for lunar eclipses anymore. We can actually go up into orbit around Earth and use special cameras with little filters that block the sun itself. So we can take eclipse images 24/7. And this is an example of a month of solar eclipses. What you can see in this image, this is not actually blue light. The space isn't blue. We're just coloring it blue because it looks nice. The diameter of the sun is indicated by this white circle here. Here's a baffle that's blocking light from near the sun. And what you're seeing is material streaming away from the sun in different directions. And so if you concentrate in any one direction, you can see that there's this jet of material moving away at pretty high speeds. You can see the motion of it expanding away from the sun. You can also see that it's incredibly structured. Can you see the stars moving behind the sun? Give you a sense of time scale. It takes a year for this Earth to go around the sun. And so in 365 days, we move 360 degrees, or we move around the sun about a degree per day. So if you look at these stars in the background, and the time it takes them to get from this side of the sun to the other, that's about a day. And so you can see there are jets of material. There are periods where regions where there's less material. Then every now and then, although never when I say to look at it, oh, there we go. There's a big one up there. You'll get a giant eruption. Oh, there we go here. There's a nice one there. We call these coronal mass ejections. Something like a billion tons of material flying away from the sun at a couple thousand kilometers per second. These numbers really don't make much sense, right? They're not very intuitive. That's fast enough to get from New York to LA in a couple seconds. And it's enough material that if it happens to hit Earth, it can actually cause our entire magnetosphere, the magnetic field that surrounds the Earth, to ring like a struck bell and generate all sorts of disturbances on Earth. Aircraft lose radio communication. GPS transmitters are off by meters, sometimes even kilometers, because their signal paths are distorted. And unfortunately, your cell phone, your GPS receiver in your car, doesn't yet know to tell you, hey, there's a solar flare going on, so maybe you shouldn't trust my directions for the next few hours, right? So if you're trying to land an airplane, if you're trying to deliver a package and you're trying to find the right address, you really care about that GPS working, and you should be very worried about those periods where we lose navigational capability due to these storms. Now, I showed you those coronal mass ejections flying out. I just want to show you one more example, looking close in of the beginning of a CME. Look right here. All right, so that's a coronal mass ejection erupting from the surface of the sun. This color image is not actual natural color of the sun. What we've done here is we've taken 3 ultraviolet wavelengths and converted them into red, green, and blue, just to give you a sense of the different temperatures of material in the solar atmosphere. What I'm going to do is I'm going to replay that one, just because I think it's really cool. And what I want you to pay attention for, just for kicks so you can appreciate these coronal mass ejections, first of all, just watch how quickly it goes from no motion at all to this giant eruption. By the way, each frame in that image was taken 10 seconds apart, to give you a sense of time scale. Also, if you look very closely as it erupts out, you can actually see a shock wave form and expand across the sun. It's that shock wave that goes out in front of the coronal mass ejection that can hit Earth and cause the initial disruption. But that blob that comes flying out carries strong magnetic fields, and it can wreak havoc on objects like Earth for days. All right, let's replay that. We would love to be able to look at these images and say that an eruption like that is going to happen. We don't know how to do that yet. Right? NOAA has a space weather prediction center. NASA's very hard at work, scientists around the country, at developing ways to look at measurements like this and be able to say, hey, in an hour there's going to be a big eruption. Even if we could say, 30 minutes beforehand there's going to be a big flare, we can't even say after one of these eruptions whether or not it's going to hit Earth, and if it does hit Earth, whether or not it's going to cause a problem. So there are a lot of gaps in our knowledge and our ability to predict these events. So that's the why. Let's talk about the objectives of Solar Probe to try to address all these mysteries I'm showing you, and then we'll talk about the how. So the overarching goal of Solar Probe is to determine the structure and dynamics of the sun's chromomagnetic field, understand how the solar corona and wind are heated and accelerated, and determine what mechanisms accelerate and transport energetic particles. It's a little long-winded, but it's distilled into 3 objectives. 1, we want to see how the energy is flowing from the sun into the corona and out into space. 2, we want to figure out how that incredible structure is created by magnetic fields. And 3, we want to figure out how those coronal mass ejections are accelerated to high speeds. And it's been 50 years plus since the beginning of space exploration. We have beautiful imagery from 1AU. We actually can sample the solar wind from spacecraft near Earth and elsewhere in the solar system, but we still have not been able to figure out what's heating the atmosphere, what's accelerating these particles. To do that, we need to send a probe into the sun's atmosphere and directly measure what's going on. How fast are the particles moving? How hot are they getting? Is it magnetic fields that's heating the particles? Is it mechanical waves coming from the surface of the sun? If we could just go there and measure these quantities, we could figure out what's actually driving all these phenomena. So the overall objective of Solar Probe is to get down within 10 solar radii of the surface of the sun. Just to put that in perspective, Earth orbits about 214 solar radii away from the sun. So we want to be just about 4% above the surface of the sun, deep in those eclipse images that I showed you earlier. I won't go into great detail here, but this is just a plot of what we think the typical speed of the solar wind is as a function of height above the surface of the sun. And then I'll just point out, this is height in solar radii, and it's in a logarithmic scale. This is speed in kilometers per second, also in a logarithmic scale. And so this is what we think the fastest wave in the solar corona moves at as a function of height above the sun. These are these magnetic waves or Alfvén waves. Close to the sun, they can move at extremely high speeds. Turns out the further you get away from the sun, these waves speeds drop down. Somewhere above 10, maybe 20 solar radii, there are no longer any waves that can travel from the sun into that solar wind. We want to get below that point. We want to get into a region that's still interacting with the surface of the sun so we can tell what kind of waves are in the solar corona. So that intersection sets the target for Solar Probe. We want to get below 10 solar radii. Our goal is actually 9.86 solar radii. Just to put things in perspective, here's Earth. Here's how close we've gotten to the sun before. So we'll be going about 7 times closer than anyone ever has in the past. Our timeline, we had what's called our critical design review back in March of this year. Our schedule has us launching in July of 2018 on a Delta IV Heavy. Now this is interesting. We launch in July of 2018. We're actually going to have our first encounter with the sun, although it's all the way out at 34 solar radii. That'll still be closer than we've ever gotten before, in October of 2018, Halloween to be specific. And then we're going to slowly get closer to the sun, and we'll have our final close approach in 2024. So how do we get close to the surface of the sun? It turns out that Earth is moving way too fast around the sun for it to be easy to get close to the sun. We have too much angular momentum. So we're going to put Solar Probe, which is actually one of the smaller spacecraft we ever made. It weighs around 600 kilograms. We're going to put it on the largest rocket currently available, a Delta IV Heavy. And that's going to get the spacecraft escaping from Earth as fast as we possibly can. That's still not fast enough. Instead, what we're going to do is about 2 months after launch, Solar Probe is going to hurtle just 100 kilometers over the surface of Venus. Right? We're going to actually speed Venus up just a little bit. No one will notice. Venus is going to slow the spacecraft down and bend its orbit towards the sun. And that's what lets us achieve our first encounter at 35 solar radii. Over the next 5 years, we'll continue to trade momentum with Venus. So we have a series. This is just a plot of our distance from the sun as a function of time. We have 3 encounters at 35 solar radii. We go past Venus. That brings us closer. Another Venus encounter, another, slowly letting us walk closer and closer to the surface of the sun, culminating in the final phase of our mission in the 2024 timeframe at 10 solar radii. Oops. All right, one of these images isn't rendering. Well, I'll tell you a little bit about prior versions of the spacecraft, and then I have plenty of examples of the current version of the spacecraft in later slides. So people have been talking about a solar probe actually before NASA even existed. Since we knew about the solar wind and we knew about the solar corona, it seemed like a no-brainer. If we're going to be able to send instruments into space, let's visit our sun's atmosphere. Turns out it's very hard to design a probe to enter the sun's atmosphere. So over the years, every decade or so, there'd be a new design iteration. I'm particularly fond of this one. It had a giant sort of surfboard-shaped carbon foam heat shield that would have doubled as a high-gain antenna to transmit signals back to Earth. That early solar probe and then the solar probe from around the year 2000 would have actually gone all the way out to Jupiter, used Jupiter to completely slow the spacecraft down, and then just basically plummeted down and plunged through the sun's atmosphere once at about 4 solar radii. And then if it survived 5 years later, it could go again. Ironically, those probes got too close to the sun to use solar power. The panels would melt. So they were powered by plutonium, the same way like outer planet missions like the Voyagers are powered. The new solar probe, the one that we're actually designing and building, uses this concept of the Venus encounters. So we don't have to go out to Jupiter. We don't get quite as close. We only get into like 9.5 solar radii. So we're able to use solar power. I'll just show you some highlights of the spacecraft here and then talk a little bit about the implementation. So the main thing that'll draw your eye that's different between solar probe and a lot of other missions is this front part. So this is our thermal protection system or heat shield. It's made out of a material called carbon foam. It's extremely light and it's an incredible insulator. At closest approach, the front of the carbon foam will be at about 1500 degrees Celsius. The back will be at about 300 degrees Celsius. It's only like 6 inches thick. The rest of the spacecraft, generally speaking, hides behind this heat shield. We have a bunch of long titanium struts, and then the rest of the spacecraft sort of held back from the heat shield. We have solar panels, and I'll show you the solar panels come out the further away we are from the sun. Then the closer we get and the hotter things get and the brighter the sun gets, they bend backwards. So when we're encountering the sun, just the very edges of the solar panels are peeking out from the side of the heat shield. That's more than enough sunlight to power the spacecraft. Those solar panels are going to get hot, so we need to have a way to cool them off. So what we actually do is pump water through the solar panels. Right? That water then flows into these large radiators. Think of it as the radiator on your car, right, with one important exception. When you're driving on the highway, air blows across your radiator. Right? Or if you have the CPU in your laptop gets hot, maybe you have a little fan that turns on to help it cool off a little better. Well, there are no fans in space. You just have to rely on the fact that space itself is extremely cold and you radiate heat away. So we need very large panels that we pump the water through to keep it cool. Interestingly, when we're far from the sun, we have the opposite problem. The water would want to freeze. So one of the reasons the solar panels are all the way out when we're far from the sun is to warm the water in the radiator system to keep it from getting too cold. The whole spacecraft regulates its own body temperature, almost like a mammal would. So when we launch, we'll immediately deploy the solar panels. We've got instruments bristling all over the spacecraft. There's a telescope that's going to take images looking out from the side of the spacecraft. Here's one of my instruments here. We're going to sense very precisely the magnetic fields from the sun. Unfortunately, we don't want to measure, well, we don't want to report back the magnetic field of the spacecraft. So we need to put that on the end of a very large boom to get it as far away from the spacecraft as possible. Once we've completed that initial deployment, those are all the mechanical moving parts, and we can begin our commissioning and solar encounters. My instrument suite, I won't go into this in great detail, but one instrument which I'm going to talk to you about a little bit about now is called the Solar Probe Cup. And then our other instruments sit in the shadow here and here. And their role on this mission is to sweep up ions and electrons and look at the directions they're coming from, how fast they're moving, how many of them there are, and let us read out and report back to Earth like things like the density, temperature, pressure, velocity, flow angles of the solar wind. Right? We want to be able to see, how fast is the wind going, which way is it flowing, how much helium is there in the solar wind, how much is that varying. And if you think back to those movies of the coronagraph that I showed you, the solar wind tends to flow away from the sun. So one of our challenges on this mission is, 90% of the time, the wind isn't going to be coming at an angle, it's going to be flowing straight away from the sun. So if we want to capture that solar wind and see how hot it is and what direction it's flowing, how dense it is, we need to be able to look straight at the sun. So in addition to some very sensitive, sophisticated instruments that sit in the shadow, we also had to come up with a very robust instrument that could actually sample the solar wind while exposed to levels of sunlight about 500 times brighter than what you'd experience on Earth. The front of the instrument will actually be glowing red hot during each of the encounters. And I think we have a little animation here of what we've gotten ourselves into. So there's the solar probe cup. And so it's designed to collect samples of solar wind flowing straight away from the sun as we go throughout our orbit. As you can see from here, the rest of the instruments, the solar panels nicely tucked back so they're not exposed to the sunlight. So I'll just end now with a little bit about the solar probe cup. It's one of my instruments, so I'll show you some baby pictures and just give you a sense of some of the thrills, some of the challenges, some of the excitement of coming up with and then demonstrating an instrument like this can actually survive this kind of unique and unusual environment. So the solar probe cup, here's a picture of our prototype that we developed before our critical design review. It's composed of a sensor and then an electronics box. The electronics are far enough away that they can hide behind the heat shields. They don't get very hot. They're basically at room temperature. The sensor itself is made out of a whole assemblage of fascinating materials that we learned about working with people who designed jet engine afterburners, nuclear reactor fuel rods, rocket nozzles. We use all sorts of interesting alloys and metals that can operate at very high temperature. We also, unfortunately, have to be able to develop and sustain high voltages within this instrument. Basically, and if you're curious, I can tell you the details afterwards, but what we do is we use a very high voltage to set up a very strong electric field. And then we measure the number of particles that are able to make it past that electric field. And then we just raise the electric field up and count the number of particles as a function of the strength of the electric field. And that lets us take an inventory of how many particles are moving at different speeds, what directions they're coming from. A little bit of math and analysis, and you get the velocities, density, and temperatures that most people are interested in seeing. So inside the instrument, one of our favorite things is this grid in the center of the solar probe cup sits at 8 kilovolts at very high voltage. And so it also sits at around 1,000 degrees. So what we use are tiny sapphire pins, synthetic sapphire crystal, that hold that grid in place so it can stay at 8 kilovolts without arcing to the rest of the instrument. We use sapphire actually at a bunch of different places within the instrument to isolate our sensors. Our sensors on this instrument are very simple, just a bunch of metal plates. And that was important. If we're going to go to such a harsh environment, we need something that isn't susceptible to radiation, that isn't going to melt. And so since all we're doing is counting particles as a function of energy, we're just measuring current, so we can just use metal plates. A lot of challenges here. You can't just buy coax cable and string it up to this instrument to deliver those high voltages. Even the cables have temperatures running between 1,000 degrees and 300 degrees. After we were selected, I visited some members of the fusion community thinking, okay, pass on to me the collected knowledge of fusion reactors and how to get things to run at these high temperatures and voltages. And basically the response was, wow, that sounds great. Let us know what you figure out. So we do things that we've had to develop ourselves, like we grow tubes of sapphire crystal. We then encase them in sapphire donuts, and then we laser weld niobium tubes around it. We laser weld because you can't solder or normally weld things when they're going to be heated to 1,000 degrees. The solder would just melt. And I'll just close with a little bit about how we test these things. So you start out, you test things in a big fancy oven. That allows you to answer a lot of basic questions. Will this still be a resistor when it's that hot? Is it just going to melt? We had a few tests where we opened the oven and we had a sad melted pile of instrument prototype. But to do realistic testing, we need to illuminate this instrument with the actual levels of sunlight we're going to see at different distances from the sun, up to nearly 500 times the brightness at 1 AU, or Earth's orbit. So one of the ways we did this testing was we went to the largest solar furnace in the world. This is a furnace in southern France in the Pyrenees. It can focus up to 10 megawatts of sunlight through these doors into a little vacuum chamber on the side. So the whole mountainside is covered with tracking mirrors. This isn't like a fisheye lens effect. The whole 7-story side of the building is shaped like a big parabolic focusing lens. So that lets us do our first demonstrations that we could come up with the materials that could survive. But as my colleague, Jay Bookbinder, pointed out, the problem with this solar furnace is the sun sets at night. And so how are we going to test for a multi-day encounter with the sun if you have to turn things on and off every day? And also, what do you do if there's a cloud that passes overhead? So over some cocktail napkins at, I think, Frankfurt Airport, we came up with this idea of buying used 70mm IMAX film projectors from movie theaters. They use short arc xenon bulbs that have the same brightness temperature of the sun. The xenon is heated to about 6,000 degrees Kelvin. Instead of letting the light diverge out like you're projecting onto a movie screen, what we do is we have water-cooled lenses that convert that light into parallel beams. One projector isn't bright enough, but by using 4 projectors and then using some water-cooled optics, we're able to combine the light, send it through this water-cooled window in this vacuum chamber, and irradiate our poor and unsuspecting instrument. And so I'm just going to end with a final test that we did. Here's our prototype of the cup. And here's a movie of the cup sitting at around, let's see, 10 solar radii from the sun, performing quite happily, getting up to high voltage. All right, so with that, I'm just going to conclude by saying, we're 50 years in the space age. We still haven't figured out the physics responsible for the high temperature of the solar corona or the shape of the solar wind. We need our direct measurements in order to answer those questions. The solar probe is going to give us those measurements. It's going to transform our knowledge of the solar corona and the solar wind. Our launch is just 3 years from now in the summer, so please stay tuned and follow this exciting project. Thank you.
Thank you, Justin, for a great talk. We have time for a few questions. If you have a question, please raise your hand and we will have a microphone to you. Great.
What are the current best theories as to where the heating comes from in the corona?
What are the current best, oh, there's a microphone, I won't repeat. So there are a lot of theories. They tend to fall within 2 camps. Camp 1 is that you have some kind of wave that's generated near the surface of the sun. And the entire surface of the sun churns in and out on the kind of a 5-minute time scale. It's like a boiling pot of water. So there's a lot of mechanical energy that's being introduced there. It's possible that some of that mechanical energy is able to travel up before those waves like damp and break. And maybe they can make it a few solar radii up away from the sun before they dissipate and then locally heat the plasma up to high temperature. The other camp is you saw how there was really hot plasma of the sunspots. And I said, well, you can't see magnetic field lines, but they're holding that hot plasma in place. So the other idea is maybe magnetic field in the solar corona is hitting other magnetic field, explosively canceling out, billions of times a second distributed all over the place, and that's heating the atmosphere. I think it's going to be both. We need to just figure out the relative proportion and relative importance of both. And it could be that the relative importance of big mechanical waves and magnetic fields changes depending on what type of solar wind you're in. But that's why we have to make these measurements. What is the magnetic field doing? Are there any waves? Are the waves getting any stronger? When the waves go away, is the plasma hotter or cooler? Those are the basic questions that we'll answer to figure that out.
Hi, thank you. Fascinating talk. I had a question about the high energy environment around the sun and the associated small wavelengths associated with that energy. So in that type of environment, EMI could become a big concern, electromagnetic interference. So my question is, how do you deal with EMI issues, and also how do you navigate when you're operating in
such a crazy environment? Yeah. Oh, great questions. So I'll answer that in two parts. One, electromagnetic interference. So the electromagnetic fields from the sun itself are not strong enough to perturb like the orientation of the spacecraft. But the electric field and magnetic field instruments on the spacecraft are extremely sensitive. Right now, they don't have to be necessarily quite as sensitive as instruments, near Earth, because everything's stronger closer to the sun. But we have to be incredibly careful not to generate our own noise that can sort of blind the electric field and the magnetic field instruments. So we're constantly doing things with our prototypes called like sniff tests, where someone will come with a very sensitive meter, and go around our instrument and look for any emission. And we're very careful that everything is synchronized on the spacecraft. We share one clock, and all the decisions of all the instruments are made on that clock, so we don't, have signals at very different frequencies. In terms of navigation, there are a lot of challenges to this mission. The photon pressure is so strong that close to the sun that left to its own devices, light would flip the spacecraft around in under 30 seconds at closest approach. So we have a momentum wheel that's constantly speeding up to keep us pointed at the sun. We have star trackers to look at constellations to make sure we're pointing in the right direction. There's always the risk that one of those coronal mass ejections that I think is great is going to happen when we're at closest approach. And in the worst case, it could blind the star trackers for a couple days. So we have an inertial gyroscope system as a backup. There are 3 flight computers that are constantly fighting each other over who's right. And the idea is the system's designed, hopefully, to be redundant enough that if we are blinded by a solar flare, we'll realize that, we'll ignore the star trackers, we'll switch to the inertial guidance and hopefully pop out the other side of the sun in one piece. It's a big challenge. And anticipating the problems is a challenge.
Very nice talk, Justin.
Thank you.
What you see in the solar wind is going to depend upon what you're flying over on the surface of the sun. Do these closest approaches happen at a time when you can actually observe the surface of the sun?
Yes, so one of our requirements is that certain number of the encounters, and in particular the closest encounters, all occur during times where the region of the sun we're flying over is visible from Earth. So maybe we'll have spacecraft operating at other locations than just Earth's orbit around the sun, but we don't want to make that assumption. So we feel like the most likely place we'll have a lot of good solar observatories in 5 to 10 years is going to be Earth. Yeah. So the dynamics of the orbit is very challenging.
Hi, thanks for the talk. My question was regarding the image and animation you showed of it was a false color sun, and it showed the coronal mass ejection. I was wondering, when you take that image, and if you process it quickly enough, I guess, that's the time that the photons arrive at Earth. And I was curious if you can use that as prediction, and if the charged particles that disrupt our atmosphere can be predicted. Like, how long does that take to arrive after that?
Excellent, excellent. So light from the surface of the sun takes 8.5 minutes to reach us. Unfortunately, the most energetic radiation is traveling at nearly the speed of light. So, the photons get here like 0.001% faster than the high energy particles. The shock wave, that big eruption itself, can take 2 to 3 days to get here. I mean, there's some very famous events. There was a great one in the 19th century that shut down worldwide telegraph lines for 2 days. Once the coronal mass ejection reached Earth. That one took like 20 hours to get to us. It was moving very fast. So if you see the flare and you're worried about the coronal mass ejection, you have half a day advance warning. So those images from Solar Dynamics Observatory, the images are recorded. They're sent to a dedicated receiver in White Sands, New Mexico. They're distributed to the east and west coast, and they're distributed with a latency of under a minute. And NOAA makes use of those images, constantly looking for an eruption that's about to occur. What we'd really like to be able to do, though, is, I hope we're going to get into the business of sending humans into deep space. And even if we're trying to get back to the moon, we need the ability to predict one of these events, more than a few minutes in advance. We want to be able to say, what's the outlook over the next 2 weeks? If we want to go to Mars, ideally, we'd like to be able to say, what's the outlook over the next 6 months? I don't know if that's ever going to happen. But we really need to expand the lead time that we can predict these events.
I had a question about the shock waves that are released as the coronal mass ejections are emitted. So a shock wave is a concentration of pressure, which seems to have similarities to sound, because sound travels as a compression wave. So I wonder, is it possible during this mission to actually hear the sun because of the pressure waves that are coming off of it?
Yeah, so now we're getting to my bread and butter. Yeah, so that's one of the things that we do as a very powerful test of these different theories, is we can actually watch all these different kinds of waves going past the spacecraft. And so locally we can see, how much magnetic waves, how much sound waves, that relative mix tells you important things. But actually, you hit on something really cool the spacecraft will do. Those shock waves, sometimes when they're strong enough, they actually generate radio waves. And the radio waves come out at a frequency that's only a function of the density of the plasma at the shock wave. So we have big antennas on board that can detect the radio waves. It's really, at and below like tens of megahertz. But one way people search for when those waves occur is they actually speed up the sound and turn it into an audible recording and listen to it. But yeah, so we should be able to hear those shock waves from the radio emission.
You mentioned that sunspots were much cooler than the surface of the sun normally. Is the actual atmospheric environment hostile enough that we'll never be able to take advantage of that with a probe? Can we ever get close enough to make use of that?
Oh, I like that. So, one of the challenges is just the mere act of getting there. So you might be able to hover or pass over a darker region that's maybe 1,000 degrees cooler, but on your way there, you're going to see the whole solar disk. So there'd be a lot of energy you'd be absorbing, and then it would be less bad than it would be otherwise over the sunspot. Of course, one other issue with the sunspot is it's cooler because it has a magnetic field that's like 1,000 times stronger than Earth's magnetic field. So you'd have to make sure your electronics didn't react adversely. But I like where you're going. I think we need a solar skimmer, solar surfer.
Okay, so please join me in thanking Dr. Kasper for an excellent seminar.